Okay, chapter 13, you guys also asked me to do number 54, which is on page 646. It says that at some super hot temperature, oh no, a particular temperature, no, that's 56, 54, at 25 degrees Celsius, K for this reaction is equilibrium constant. K is 0.090. And they've given us two scenarios. That makes this kind of a longer problem than it otherwise would be. They've told us that in part A, they gave us reactants, no product. And in part B, they gave us product and no reactants. So it's pretty straightforward. You still have zero on one side or the other at the initial. So we're going to be making some ice diagrams. But first, if we start for A, we need to figure out what our concentrations are. They've given us, our equation is water plus chlorine oxide is giving us HOCl, 2HOCl. So they give us 1 gram of water and 2 grams of this chlorine oxide, and so we figure out your molar mass. So I took my 1 gram of water divided by 18.02 for the molar mass of water, and I get 0.055 molarity of water. That's concentration of water. Concentration of the other one's 2 grams divided by its molar mass. All of this I'm setting over 1 liter to make it equal to concentration. So nice they gave us 1 liter for that. So now that we have those concentrations, I'm going to set those up as my initial concentrations, or my I. So 0.055 molarity for the first reactant, 0.023 molarity for the second reactant, and 0 for initially what our concentration of the product is. There's going to be some change, so we're going to write those down as our X. We don't know how much they are going to change, and we don't have any idea what our new equilibriums are, except that we know in the end they are going to equal, if we use our mass law, we're going to get our 0.090 for our equilibrium constant. So these are going to decrease by X. This is going to increase by 2X because the balance equation told us we're going to end up with 2 moles of this for each mole of reactant. And now I'm going to, in the equilibrium, once they're at equilibrium, I have to combine these terms where I'm going to take this plus the change, which is a negative, and this plus the change, which is a negative X, and 0 plus 2X is going to give me 2X for at equilibrium. These are my concentrations at equilibrium. So now I'm going to have to set up my equilibrium constant. And that's going to take a little more room than that piece of paper. So 0.090 is going to equal concentration of my product, which is 2X squared. Or I have to do it right away because it's just going to drive me crazy if I don't. 4X squared. And all of that is going to be set over my reactants. Cha-ching, 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 right? And those are 0.055 minus X and 0.023 minus X. Now I have to set this up. I have to set it up to 0 at some point or another. So we're going to have to FOIL these two on the bottom of this fraction. So I'll just keep this 0.090 here, and I'll keep this 4x squared up here. But now let's FOIL this. 0.055 times 0.023 is, I'm going to put this all in one big parentheses. Oh boy, this is why they did it in scientific notation in your book, because this gets pretty long decimals here. 114 minus 23x is going to be in, and out is going to be minus 0.055x. If I combine those, I end up with minus 0.078x. I think that's right. Okay. Oh, and then we get our x squared. Negative x times negative x is positive x squared. Now I need to multiply both sides by that. And as I multiply it over here, and this is going to set it equal to 4x squared. So 0.090 times 0.00114 Maybe if I don't round it yet, I'm still going to end up with... Can I just start 1, 2, 3, 4? Pretty much. How is that going to stay the same? One, 4. I got too many ones here. Sorry. Times 10 to the negative 4th. Minus how am I going to end up with a positive x? 7.02 times 10 to the negative 3rd. X plus 0.09 x squared. That's just distributing that across those three, bringing them up here. Now I gotta set it equals 0, so I'm gonna bring my 4x over here. Although really it would be easier if I brought all of this stuff over here so I can keep a positive x squared. So that's what we'll do. We'll say 4x squared minus 0.09 is going to equal, I'm just going to, why am I writing 4? I don't know, because it's going to be 3.91 x squared plus 7.02. Now that's going to be positive. That's nice. 7.02 times 10 to the negative 3rd x minus 1.14. Now we just use our quadratic formula. And negative 7.02 times 10 to the 3rd plus or minus 4.93 times 10 to the negative 5th plus 1.78 times 10 to the negative 3 to the 1/2 power all over 7.82, which could equal 4.6 times 10 to the negative 3rd or negative 6.4 times 10 to the negative 3rd, but negative doesn't make sense for a concentration of x or 2x. We can't end up with less than 0 on our product side if we look back at our original ice diagram. We have got to have a positive x over here. Okay, so 4.6 times 10 to the negative 3rd, I think. Yeah. Or I could say 0.0046 equals x. And now just look back, what are they asking for? Again, concentrations of all species at equilibrium for each of the following cases. So we just take this x we have got, And we plug it back in here. 0.055 minus x is going to be 5.005. So basically it's 0.055 minus 0.005, which is going to be 0.05. And that is our concentration of, oh, I should make this a molarity. And that's our first one that I had listed, which was our water. That's our H2O. It's 0.05. And then our water, that was our water. Then our chlorine oxide is going to be 0.0230 minus X. So minus 0.005 if I round it. Or 4.6, which is going to be 0.0018. 23 minus 5? Yeah, 18. So Cl2O equals 0.018 molarity. And then 2x, that's probably the easiest one, is 0.092. HOCl. Isn't that what we're making? Yep. All right, and that's how you do A.